Okay, so in this next video, we're going to do some focus on this one's just one direction, changing Cartesian equations into polar equations. So let's just start with something simple as a line, which turns out to be much better, more easily stated in the Cartesian plane than in the polar system. But let's see how the conversion works. So we know y equals r sine theta. We know x equals r cosine theta. So we're going to substitute. So this is going to be r sine theta equals 3r cosine theta minus 2. Now to get it into kind of an r theta format, which is what Desmos requires in order to be able to see it, we need to do some manipulation here. So I need to get my r terms together so that I can isolate r, because at the end I want to end up with r equals. So I'm going to subtract 3r cosine theta is -2. I'll take the r out. I have sine theta minus 3 cosine theta equals -2. And finally, I divide by the thing that's multiplying r. So sine theta minus 3 cosine theta. That's what I'm dividing by. So this should end up giving me this, which we know has a y-intercept of -2, has a slope of 3. So let's take a look. -2, I gotta write that down, or I'll forget it. -2 sine theta minus 3 cosine theta. Okay. So let's take a look here. Back to Desmos. Take this off, get rid of this guy. Let's switch back to polar. Okay. So we said r theta equals -2 divided by, and we had sine theta minus 3 cosine. Great. Okay. Well, it definitely makes a straight line. And what else can we say about it? Let's put the 0.0 -2 on there. Okay, wrap it up in parentheses. Okay, that's definitely on the line, so that's a good sign. And then let's just use the slope. So if we go over 1, we should go up 3. So there should be another point on here, 1, 1. And there it is. Yep. So this is exactly it. This is the y equals 3x minus 2 line expressed in polar system. And that, of course, is, very complicated and not nice. And that's not where polar coordinates shine. Polar coordinates aren't designed to represent things like lines in a very simple way. Let's do another one. Something which has some circular symmetry. So what about x squared plus y minus 2 squared equals 25. So again, we can substitute. Well, actually, we can substitute right away, but I'm just going to go ahead and multiply this out. This is y squared minus 4y plus 4 equals 25. Because one of the things that I get here is r squared. And then I can substitute r sine theta plus 4 equals 25. Okay, so now, let's see. I'm going to bring everything over to one side because I have a quadratic in r. And if I'm trying to solve for r, then I need to figure out a form that's going to work. I'm just going to use the quadratic equation from here. Minus b plus or minus the square root of b squared minus 4ac over 2a. So my coefficients are 1. B is -4 sine theta, and c is -21. Okay, so I've got 4 sine theta plus or minus the square root of, and then I've got v squared, so that's 16 sine squared theta minus 4 times 1 times negative 21, so times negative 21 divided by 2. Okay, so 4 sine theta, this is r equals, plus or minus the square root of 16 sine squared theta plus 84 over 2. Okay, so it's giving me 2 roots here. Let me just look at one of them and then we'll kind of see where the other one comes from and if it matters. Write down again because I can remember that. There is a common factor of 4 that could clean this up, so actually might as well do that. There's a common factor of 4 in this, so I can factor that out. Let me just do it over here, compartmentalize it a little bit just so you can see what's happening. So I've got the square root of 16 sine squared theta plus 84. If I take 4 out, it's 4 sine squared theta plus 21. So the square root of 4 is 2. And that leaves me with the factor 2 to cancel there. So r equals 2 sine theta plus or minus the square root of 4 sine squared theta plus 21. Oh, cleaned up a little bit. So back to Desmos. These points out of here. All right, so my r function is 2 sine theta plus, I'll do the positive version first, square root of 4 sine squared theta plus 21. Okay, and like that. Too many variables. Try dividing ISN. Oh, because it doesn't like the fact that I did that. Okay. Sine theta. Oh, because I spelled this wrong. That's why. That's no problem at all. There we go. Okay. So this is a circle. And it's the same. We can check our work. We've got x squared plus y minus 1 squared equals 25. Yep. Oh, wait a minute. Did I mess up? Those are not exactly the same thing. Let me double check my. Oh, it's y minus 2. Y minus 1. There we go. Exact same thing. Right? We can switch it on and off. And basically, we'll do some work with ellipticals and parabolas and conic sections. The y minus 2 is basically a shift of going up 2. The radius is 5. See, if I took out the minus 2 here, I would have this circle of radius 5. So all the minus 2 does is it shifts it up. And interestingly, I don't need the second version of that. And in fact, I imagine that it comes out exactly the same, whether or not that's plus or minus, which is kind of interesting. So again, not super easy in terms of the way it looks. If this were just x squared plus y squared equals 25, that would come out looking very nice because basically that would boil down to this form, which is very simple, but the fact that it's shifted means it gets a little complicated in terms of how it gets manipulated and that step of solving for a quadratic in terms of another variable is often pretty confusing. Okay, one more. So let's see. Clear that up. What if I just have a simple y equals 3? So in this case, we know y equals r sine theta. So this is going to be r equals 3 divided by sine theta. Another way to say that would be 3 cosecant theta. Let's graph it. Let's see what happens. So I'm going to get rid of these two. So r equals 3 divided by sine theta. And there it is. So horizontal line, straight across. It's kind of amazing. Very simple representation. Unlike the other line that we had that was kind of messy, but and also an interesting application of cosecant. Okay, so that's another thing that you're going to need to be able to do is to convert equations from the Cartesian form to the polar form. We're not really going to go the other direction, taking polar equations and converting them into Cartesian equations, because for the things that polar forms are very good for, the Cartesian forms would just be crazy complicated and would require probably multiple equations just to try to convey the same thing. And just to give you a sense of that, let's look at r equals 3 plus 2 sine 5 theta. So there's a polar graph. And it's a little hard to imagine the y equals format of this. I mean, first of all, there's no way to write it as a function because of all of the different violations of the vertical line test that you can see here, right? Even these close branches have violations. And if I draw a line, here, I've got so many different violations that you got to think about breaking this up into all these different parts. So Cartesian just doesn't make any sense as a way of describing this here, and you wouldn't be asked to do that. What's coming next is just looking at some different families of polar functions, looking at symmetry and kind of thinking about those ideas. All right, see you in the next video.